Fun with gravity.
Gravity already? But just to review, all right? If I take a book and a piece of paper and drop them, all right, obviously the book is going to hit the ground first. If I ball up a piece of paper, though, in the absence of air resistance, or this paper is not as affected by air resistance, it falls at the same rate as the book. All right, bring me the book again. One more. At the bottom, the book did take a little bit of a lead. If I use the book to push the air out of the way, where air is not a factor, you'll see that they both fall at the same rate. Gravity causes things to accelerate at the same rate if you ignore air resistance. All right, bring everything up. All right, so Isaac Newton described gravity as a force acting between two objects. So if you drop an object or you jump, then the force is acting between you and the earth. You have a lot less mass, so you're the one that undergoes the greater acceleration. Einstein came along and enhanced our understanding of gravity by saying what's really occurring is not that there's something pulling objects together, but that things with mass actually warp space-time, which causes things to move in straight lines through curved space, which I'm going to try to demonstrate on a trampoline.
Behold, the law of universal gravitation.
Any object with mass attracts every other object with mass in the universe with a gravitational force between them. So if these two objects were out in space with no other forces acting on them, there'd be a force of gravitational attraction between them, which would make them move towards each other. The ball that's lighter would undergo the greater acceleration. All right, now all that's well and good, but Einstein enhanced our understanding of gravity by saying that what gravity really is things with mass distort space-time, and what we experience as gravity, that force that pulls things towards each other, is really things moving in straight lines in curved space. And we're going to try to represent that here, this four-dimensional space-time, with a three-dimensional trampoline, which is one of the best ways, I think, to try to look at this. So I'm going to place this object with a lot of mass, and I'm going to stand right next to it. We are warping the trampoline. That's like warping space-time. Here's another object in that space-time. If I set it down, it's going to come towards us. This is what happens with gravity. Objects that have less mass undergo a greater acceleration. They're moving in straight line paths, but it's not because of some invisible force pulling them. It's because of a distortion in space-time because of the more massive objects. So if I put this down, it's going to move towards this massive object, which is me and this medicine ball. So my body, let's pretend that that is a massive object like a planet. I am warping the space around me. So if I have a lighter object like this ball, which represents a moon, an object like a moon is going to have a tangential speed, and it's following curved space. So it's not so much that the planet is pulling in on the ball, it's that the ball is following a curved path in the warped space around the planet. And if it wasn't for friction, this ball would keep its speed up and it would continue to orbit around the planet. All right, I can't get rid of friction on this trampoline, but you can see how the ball orbits around. We're here to demonstrate that you are actually longer when you lie down than when you stand up because of gravity compressing the discs in between the vertebrae in your spine. So what we're going to do is we're going to make a measurement here of Skylar while he's laying down. Let's see. So we're going to take this piece of 2x4. I need you to move your arm, sir. Here he is. And I'm going to mark his height, lying down.
Shut.
All right. I am marking him right now. Hold this. All right, we're back. And we now have him standing up with his back against the wall, perfectly straight. We're going to mark him standing up. Hold this. And we're going to try to mark this.
Going to jail, baby.
All right. And now, let's take a look at those two marks. Step away. This bottom one is the one I just made with him standing up.
Oh.
This was him lying down. So he's almost, according to this, about an inch. We did this before, and it was a little less than that. It's not perfect. The boards are not 100% straight. But when you do this, you should find, with a little bit of margin of error, that when you are lying down, so this is the lying down, all right, and then this standing. That when you are lying down, you are a little bit longer than when you stand up. This is the lying down measurement. This was the standing up measurement because of gravity. Measurements from the first time we did this. It's got a little crooked on me, but we still got a difference. The lower line was standing up and the higher line was lying down. So even though the method of measurement was not perfect, we've done this a couple of times, and in both cases we had the length of Skylar was longer when he was lying down than when he was standing up.
Bonus feature!
Welcome to the bonus footage. I want to talk to you about something called angular momentum. You can think of it as rotational momentum. Now, we've already talked about linear momentum, which is mass times velocity. And mass is directly related to the amount of inertia. More inertia, more mass. So here, we're going to talk about rotational, or as it's actually called, angular momentum, which is the product of rotational inertia and rotational speed. Now, your rotational inertia can change depending on how you hold your body. And the thing about angular momentum is it's conserved in the absence of outside forces. The total angular momentum stays the same. That means if your inertia goes down, your speed goes up, and vice versa. So here I'm going to demonstrate this and get a workout at the same time. So I'm going to get myself spinning with my arms out, which is going to give me a high amount of rotational inertia, bring them in, which decreases my rotational inertia and increases my rotational speed. So first I'm going to get spinning, then pick my legs up off the floor. All right. Decrease inertia, increase the speed. Increase inertia, decrease the speed. Decrease inertia, increase the speed. Another way to look at this is the less inertia, the easier it is to rotate. The more inertia, the harder it is to rotate. So we get spinning again. A lot of inertia, harder to rotate. Less inertia, easier to rotate. Harder, easier to rotate. And without even touching the ground, I can change my spin rate and get a workout at the same time. Decreasing my rotational inertia, making my speed increase. Basically, decrease the rotational inertia makes it easier to rotate. I'm going to tuck my arms and legs in, decreasing my rotational inertia, thereby making it easier to rotate and conserving angular momentum. Here we go. All right, gainer boy. Yeah, I got that.